This is Mario Party DS, one of my favorite childhood games. But actually playing the game? Nah, that's for losers. I want to destroy the game using AI and image recognition. There are 73 minigames in Mario Party, but not all are interesting to automate, so let's see what we got. The first one I decided to take on is Star Catchers, a game where you have to tap on the appearing stars as fast as possible in order to catch them. You are playing against 3 other players who are also trying to catch the same stars, so whoever is fastest gets the point. The logic to automate that seemed simple enough, but I needed to do some setup work first. I need to run an emulator with the game and capture the screen region of the touchscreen continually and as fast as possible. That way I can write a function that receives the newly captured screen image and can analyze it. I used the popular screen capture library MSS for the job and set the coordinates for my emulator screen. After that, I chose a capture frequency of 30 FPS and set up a function that gets called on every capture. In it, I can write my logic to play the game. Could I use a higher capture frequency like 60 FPS? Yes, but you have to remember, whatever logic we are running has to be done in less than 1/60th of a second. So depending on the game complexity, it might not be the best idea to use a large amount of FPS. For Star Catchers I picked 30 FPS, which should be more than enough. Anyway, now it's time to program the game logic. Detecting incoming stars is actually quite easy. You see, except for the stars, nothing else changes on the screen, if I choose the region to exclude the timer at the bottom. That means if I subtract the current frame from the last one, we should only see what changed, the stars. OpenCV, a popular computer vision library, provides us with all the required functions to solve this problem. Here you can see an example. I chose 2 frames for the difference, one with a blank sky and one where a star appears. Taking the absolute difference, we can see everything turns black, except the regions where the change appears. This effect can be enhanced by turning every pixel fully white that is greater than 0 in the difference image. Now, there are a few things left to do. Detect the center of all new appearing stars, loop over their centers, move the mouse and click. The detection can again be solved by OpenCV. We can find all contours of the stars by using the aptly named findContours function. It takes an image and returns the list of all outlines for continuous pixel regions. Taking the center of each contour, I now have the locations of all stars that appeared during that frame. Using this information, I can move the mouse to these locations and click. Running the program, I could see the mouse was moving properly, but for some reason I didn't get any points. It turns out my program's clicks were too fast and I actually had to delay them a little bit for the emulator to register them. After pausing for just a few milliseconds, everything worked fine. Here's me playing against bots of the highest difficulty. I'm Waluigi. I love how at the end all the stars are blinking and the bot is still trying to click on them all at once. But now let's see what we're doing next. I decided on Goomba Wrangler, which is the first game of Mario Party DS. In it, you have to draw small circles around Goombas to catch them. Towards the end, yellow Goombas appear that are much faster than the brown ones, but give 3 points each. If you accidentally circle around a bomb, however, you lose half of your captured Goombas. Automating this game is much more difficult than Star Catchers, as you not only need to detect change, you also need to differentiate between Goombas and bombs and draw circles around them instead of just clicking. There are several ways you could go about solving the detection, like pattern matching or object segmentation using YOLO. I opted for a much simpler approach though, detecting colors. Since the Goombas and bombs are quite distinct from the background in terms of color, it should be easy to just look for clusters of brown, yellow and black to get locations of all entities on screen. To find out which colors exactly I had to look for, I simply took screenshots of the entities and loaded them at the start of my code. I then applied a slight blur to them to get rid of any potential artifacts and found the upper and lower color values, which I will use in the detection. Using these color ranges and the findContours approach from before, I can now differentiate between Goombas and bombs. With that knowledge, I can now attempt to encircle the Goombas. I opened my old math textbook to figure out how to implement a circle function. Given a center and a radius, it returns a list of n points on a circle. When the mouse follows these points, it's basically drawing a circle, and the more segments I use, the smoother the circle becomes. Let's hook up the mouse and see how it goes. It looks like the capturing is working, but we really need to take care of the bombs now. An easy solution is to basically span a danger region around them, based on how fast they can walk and the time it takes us to draw a circle. To do that, I just had to filter out all detected Goombas that are within the reach of the bombs. In addition, I noticed that captures around the edges of the screen fail often, so I ignored all Goombas that are too close to the edges as well. The detection window now only shows Goombas that match the criteria. I also sorted them by distance to the bombs, so we take the least risky Goomba first, which you can see by the rank numbers. And that actually worked. We successfully won against the expert AI, but only barely. There are still a few optimizations on the table. The yellow Goombas are way too fast for our method, because drawing a circle takes too long. I simply removed detection for them, because we can get more than enough points with normal Goombas. Next, I fiddled around a bit with the bomb and wall boundary parameters, as well as with the circle radius and draw size. I arrived at a solution that absolutely crushes the expert AI. Enjoy the show. Pretty nice, but not perfect. I also experimented a bit with position extrapolation to predict future movements and make optimal captures, but it turns out that would be a video on its own. So let's check out the next game for now. Study Fall is a reaction game where you need to press the A button as late as possible before hitting the ground. When you press too late, you get 0 points. Automating this game is relatively simple. I just set up a small 10x10 screen capture region and looked for one exact ray value within it. And of course, when the color is detected, I press the A button. And this time I actually cranked it up to 60 FPS, because the capture window is much smaller and there's basically no logic happening. For the output, I scaled up the captured image and added a hit indicator. Red means the color isn't detected and green means it is. Let's give it a try. I can't believe that this worked first try, but we can do better. By moving the detection window up a bit, we are essentially waiting a bit longer before pressing A. After a few tries, I landed on a solution that almost always gets the perfect distance of 0 centimeters. Very nice. Let's see what the next game will be. Well, I guess the video is over already. I prepared a few more games, but they will have to wait until the next video. Subscribe to not miss them. And if you are at all interested in deep learning, I made a really cool location detection AI for Counter-Strike 2. Check it out next.